Okay, actually, welcome back to this session, the afternoon session. The session will be recorded again as in the morning, and then it will become available later. So this afternoon we have 6 presentations and no break, but the good news is that we'll finish at around 3:30, so we can have our break then. This afternoon, the focus is on electrical distribution systems, and then about low carbon, I suppose, in the construction industry and buildings. So without further ado, I think I would like to introduce our first speaker, Mohamed Darwish, who is going to talk about power electronics, smart distribution systems. And Mohamed, you and everybody else, you have about 15 minutes. I'll keep an eye on time so that we can have everything within the time and have some time for a couple of questions after each presentation. So thank you.
Thank you very much, Maria. Okay, let me share my screen, and I hope you can all see my screen. Is that correct?
Yes, we can see it.
Perfect.
And
Okay,
now it is on presentation
in
mode.
the
Yes.
presentation mode. Okay, perfect. Good afternoon, everyone. I will try to keep my presentation quite short as well, and I will try to not to go very technical as well. So try to make it as generic as possible there. The title is Power Electronics in a Smart Distribution System. Now, a lot of people, they don't know what is power electronics. Power electronics, a very simple definition, is using electronics in order to control the power or energy. Now, this is the sort of like, the well-known definition. My definition is slightly different. Definition of power electronics, in my opinion, is where is the money? Power electronics is there. Okay, so we follow the trend of the research, whatever the research area. So if it is in electronic or energy or control, we are quite happy to move into that area. Okay, why now? Why suddenly, over the last, say, 10 years, there is a booming on the power electronics? There are so many reasons. First of all, there is development of fast semiconductor switches that was not available in the 80s, 90s. Nowadays, we have a lot of very fast and very powerful one as well. So I'm talking about fast as well as high power semiconductor switches. And also the widespread of microcontrollers. If you remember 20, 30 years ago, how, to find a suitable microcontroller was nightmare. It was very expensive. Nowadays, they are so cheap and very easy to use. Even the kids at school, they use microcontroller for their projects nowadays, and they are quite powerful. Also, development of modular power electronics. So we can have a circuit now where the controller, the protection, the power devices all integrated together in a modular system. So that's why the power electronics became very popular nowadays. Perhaps over the last few years, there is what we call it the wide band gap semiconductors. They are available at very high voltage and they can withstand very, very high temperature. So this is a major breakthrough within the power electronics devices. Okay. Another things, we have the IGBTs, isolated gate bipolar transistors. This is a big breakthrough. It has been around for more than 15 years. The voltage and the current level, we're talking about up to 1200 amps and 4.5 kilovolts. Okay. Now, until 2 years ago, the prices was very, very high. The price is still high, but suddenly over the last year, for those who are doing practical work in universities and so on, we have a new IGBT came out in the market, and it can withstand 1200 volts and can carry 75 amp, which is very high voltage, very high current, and the price is less than $5 compared to the $3,500. Okay, so the prices came down, especially for practical work where a lot of my students already using these sort of IGBTs. Microcontroller, there are so many variety, the PIC, the ARM, the AT51, there are so many of them, and the prices again became very, very cheap, and they are very powerful, very fast. So that enabled the power electronics to do a lot of things which was very difficult to do in the past. I did mention the modular power electronics. So nowadays you can find all in one integrated. For example, you can find the maximum power point tracking within the inverter, within the DC to DC, all of them with the protection circuit, all of them encapsulated or integrated together in one part. So, you know, discrete component, although we're still using them for our student to do in the lab, but from the manufacturing point of view, they are working within the modular power electronic systems. Okay, there are two challenges. These challenges is specific for power electronics. The first one is the inverter itself. Inverter, by the way, inverter within the electronic engineering, we're talking about from DC to AC. Sometimes people with the mechanical engineering background, they call it converter, which is from AC to another AC while they have a DC link in between. Definitely the inverter is in the heart of any power electronic devices nowadays. Electromagnetic compatibility, filters, power quality, all of these are challenges within the power electronics, i.e. Power electronics sort of like challenging itself. So it's creating problems and try to solve these sort of problems there. Within the inverter, nowadays we can, when we talk about the solar or renewable energy, there are so many different applications. For example, we can have a centralized inverter where we have all the PV panels connected together via string diodes, and then we have a central inverter. Of course, has some advantages and some limitations there. And also we can have what we call it the string inverter, where the maximum power point tracking and the conversion from DC to AC is carried per string. Again, this one has some advantages and some limitations. And then we have what we call it the sort of common inverter, where the maximum power point tracking is carried out per string. And then we have a common inverter connected to the utility. Again, this one has some advantages and some limitations. And then, of course, we have the state of the art, which we call them AC module PV system, or we can call it microinverter. That means for each panel, we have the inverter is already built in the back of the panel there. And they are all connected together, and they are connected to the utility. Now, this is very popular. However, the controller it has to be challenging because a proper synchronization has to be carried out. And this is the sort of the promising option for the future. These are key measures for inverter circuits, something like the distortion, we call it total harmonic distortion, the losses, the complexity, the filter, the cost of the system, how it is controlled, what sort of frequencies operating. All of these are sort of, you know, challenges when we in the power electronics we deal with. So I know inverter looks very simple, but you know, year after year, I supervise a lot of students doing work in each of these bits of the inverter. Also, the second thing is the electromagnetic compatibility, filters, and power quality. Now, power electronics in general, they generate a lot of problems like power quality issues, electromagnetic interference, and so on. However, power electronics also can clean the mess which it generates, okay? So what we have in front of us here, this is how we deal with, you know, identifying what is the problem, and then we identify a range of solution, and then we evaluate the solution and find the optimum solution. So in a way, we create our mess, but we clean our mess as well. This is the challenge within the power electronics. An example of that is the active filter. When we talk about filters, something like nonlinear loads, which is like, let's say a computer is nonlinear load, it generates a lot of frequencies, unwanted frequencies. We call them harmonics. And then we are using the power electronics to clean this harmonic using active filters. So what we do, we actually inject harmonics opposite and equal to the one generated from the nonlinear load, and that will give us only the fundamental component at the supply. So this is one of the powerful active filter performance within the power electronics. And then, so that what I talked about, it's sort of like power electronics challenges there. And then we have general challenges. Now, first of all, we have increasing number of renewable energy sources. We have the PV, we have renewable. In the morning session, we have seen a lot of these challenges there. And then how do you manage this sort of things within the electricity grid? How to improve the power supply reliability and the quality? And what shall we do with the peak power demand reduction? However, the biggest challenge, we have it nowadays, and a lot of people did touch about it in the morning, which is for us in the power electronics, is this one. So this is the biggest challenge, electric vehicles. Nowadays, we have a lot of them coming out in the market, and the number is increasing. I wouldn't say day per day, but almost hour per hour. Now, what sort of challenges? First of all, a load demand increase. Okay, so suddenly we have a big load demand there. And then component overloading, phase and voltage imbalance, harmonic injection, all of these, they inject harmonics, power loss, stability. People working within the power system, they will understand what is, each one of them, it's a big challenge and they have to be aware of. Now, just to have an idea, what is the global electric car sales there? Just between 2020 and 2021, the number has doubled. And I'm talking about pure electric vehicle. I'm not talking about the hybrid one. The hybrid one is much higher than that. Okay, so I'm talking about pure electric vehicles. So of course, China is a major player on that, but Europe is quite, there's a big demand or big booming within the electric vehicles. Now, of course, are we catching up? Can we do something? There are two things which you have to be aware. There are two scenarios there. The first scenario, car park within the EV charging facilities. Are we ready for something like that? And if we have home installed EV chargers, are we ready for that? So what I'm doing here, I'm taking these two scenarios. That's where we're going to charge our cars. If I take the first one, EV charging facilities there, okay? So here we go. You take your car, you go to the shopping and you charge it, okay? Now, of course, we talk about the times of the shopping. It is limited within 5-6 hours. What do we need? If everyone is charging their cars, especially those who don't have a charger at home, now we're having a problem there. So we must have a proper power management based on the proportional power there. Now, also we have to look at the state of charge of the proportion there. Now, there is a study which, if we don't apply any power management there, we can see on the left hand, cars arriving, charging, and the green one in the top, this is the power demand within the specific car park there. Now, alternatively, and on the right hand there, I have the state of the charge, which is the time per minute. Now, if I apply some sort of power management there, in that case, I'm not charging the car as it comes along, but I am testing the state of the charge of the car. And perhaps if a car has, excuse me, 20%, might have more priority to the car, which has, let's say, 60% and 70%. So there is some power management is needed there. And there's a lot of work is already carried out within this area. So that will take us to the battery management storage system. We have to have the grid, and we have to have sort of the aggregator there, talking about the storage system, talking about the battery charging system. and they have to be in communication with each other in order to develop what is required there. Okay, so this is the first scenario, which you are charging your car when you go to the car park or something like that. The second one, home installed EV chargers. Now, this is even worse scenario because this is there is a study there showing that people when they go home, this is probability over sort of a typical weekday. People when they arrive at home, they arrive around 5, 6, 6:30. And assuming people they will plug their car in the electric charger to charge their cars, then we have a nightmare here. We have seen Ahmed Zoba talking about the camel diagram in the morning, how's the power demand and so on. Here we go. We have a typical one of these sort of scenarios there. Now, if I translate that into sort of the power demand, we can see the red one is the normal one without any electric cars installed. And this is a study carried out on 1,262 houses. And they found that during the time 6, 7, 9 o'clock in the evening, there is huge demand of the power there. Now, somebody working in the power system, he wouldn't like this curve at all. What they like to see this peak is chopped and moved somewhere else. That will be a much better scenario there. We call it peak shaving. In order to do this peak shaving, we have to have sort of everything talking to each other. So we have the smart grids, generator, renewable energy, energy utilization, loads, energy storage, energy conversion, and then in the heart of that, we have the energy management system. And of course, all of that has to be in communication with each other there. Okay.
Your 15 minutes is up.
Is up.
Continue,
Okay.
but yes, then
Yeah,
we'll have less time for anything
sorry.
else.
Yeah,
Yeah.
this is the last 1 or 2 slides.
Okay.
This is just some of the research I'm doing. I have 2 PhD students now working in this specific area, which is AV wireless charging, either capacitive or inductive wireless charging. And recently, as Sean mentioned in the morning, we received recently a British Council project about the UK Saudi Arabia between Brunel and King Abdulaziz University for enhancing research, network, and education within this area there. In conclusion, power electronic technology is something very important and can generate problem, but can solve the solution. EV is booming, and so is the power electronics. And thank you very much, everyone. And sorry for overrunning a bit of the time there.
No, that's fine. Thank you very much. Thank you. It was a very nice presentation. I liked your definition of power electronics and the more traditional definition as well, and quite a lot of the challenges that you have outlined. Are there any questions for Mohamed, please? Yes, Tang.
Thank you, Maria, and thank you, Mohamed, for this excellent presentation, which shows your 30+ years of experience in this subject. So my question is about the future of power electronics. So as we can see, we have a lot of electric vehicles, PV systems, and even wind turbines, they connected to the grid using converters. So what other mention is about DC microgrids. So what is your vision about, DC microgrid? Do you think it will somehow, in the future replace, the current, systems using predominantly ACs? And yeah, and what are the challenges in this subject? Thank you.
Yeah, thank you very much. Actually, DC distribution is coming more and more popular now. And we have in China so many DC distribution systems. And this is, the power electronics is in the heart of it. Actually, I was involved in a project which has 1.6 megavolt DC, voltage DC. So there's a huge voltage there. So definitely power, as I mentioned, power electronics is sort of very flexible area. So whenever there is a work, either within the energy, within the low electronics, high power, so it moves there. And, you know, thanks to the microcontroller, it gave us this sort of flexibility as well, and the power semiconductor devices, as I mentioned. Thank you, Chan.
Thank you, Mohamed.
Thank you. Thank you. I think there is another question by Savas.
Yeah, Mohamed, yeah, thanks very much for the sort of informative presentation. My question is on the wireless charging. I mean, do you have one at Brunel, or do you have one, or?
We have, you mean at Brunel? Yes, we have a small scale one. So I have to teach this student are working, but not on a proper electric vehicle. I hope one day we can achieve that, but they are doing it in sort of a small scale now. Okay, so it is like a model, but hopefully I'm, you know, with the new MSc course starting in September, and Chan is leading it. So hopefully we'll work into this area quite fast there.
Good. And the, I mean, efficiency of wireless charging, is that similar to?
No, not. It is less. It is less. However, it has the advantages that first of all, it can be charged in the move, especially for buses and electric vehicle, you know, big things. So while it is in the move, it can charge, as well as the flexibility as well. So, you know, I'm talking about, it could be like a car park. The whole car park can be wireless charging, so you don't need to plug something there. Yeah. So you are absolutely efficiency. It's improving, but definitely not as efficient as the wired charging.
Yeah, interesting. I mean, it'd be nice to have a charger for you to play with. So, so push for it. Yeah, great. Thank you.
Yeah, yes, good. I don't see any other hands. So, yeah, thank you very much, Mohamed. And we will move on to the next presentation, which is going to be delivered by Ioana Pisica. And she's going to talk on the improvement of energy efficiency in electrical distribution networks. So, Ioana, it's okay. We can see your presentation. So you can start, yeah.
Thank you very much for the introduction. As Maria said, I will try to tackle the problem of improving energy efficiency in distribution networks. So as we will see, the power system is made up from different systems, but distribution networks are the area where I've been focusing in the last 10 years or so. And this is why I chose to discuss about this. And also one project very relevant to this area, which is current, and we are underway as we speak. Now, in simple terms, the operational aim in power grids since the advent of such system has been to balance the generation and demand, actually to make sure that generation follows demand so that loads don't have to be switched off because we don't have enough generation. So again, this is a very simplistic way of describing it. But in the past, the generation was composed of large power plants, and these were connected mainly at transmission levels. So the power system is made up from transmission system, which is at high voltage and very high voltage, and distribution systems, which are the lower voltage grids, which come into our homes ultimately. And as the generators were connected to the transmission system, the focus was in the past on managing assets in transmission systems so that we can play with the power generation and to cover the demand. Mohamed had a slide also showing the demand curve and how we want to shave the peaks. So we want actually to make our demand more predictable by reducing the variability in those peak times. But I won't get into details now about that. What I want to say is that in the last 10-15 years, with the introduction of distributed generation and more importantly, sustainable generation, renewable sources, these have been connected at distribution level, and this means that it is now more important to focus on managing assets at distribution level than it used to be in the past. And we are interested in power losses with reverse power flows, and I'm going to explain in a second what that means. We have to do voltage control, which I'm going to talk about in the next slides, and generally to improve somehow the efficiency of distribution grids. Now, this improvement of efficiency of distribution grids sounds like a single problem, but it's behind it several intertwined problems. What I meant by these reversed power flows was the fact that by having renewable energy sources, by having electric vehicles, as Chun and Mohamed mentioned earlier, we introduce electricity from the consumers, what we used to call consumers, and now we call prosumers, from producer and consumer, towards the assets of the network, which is unusual because the whole system has been built in order to supply electricity downstream from the generation to the consumers. So now we have to deal with these reverse power flows. And as I said, the efficiency of distribution networks can be decomposed, let's say, into several aspects. However, they are not disparate issues. So as you will see, as I will talk about each of them, they are connected to each other. So you cannot really have one without the other. So if we start with voltage and reactive power management, we can think about the fact that the distribution system operators, how they are called now, they used to be distribution network operators, but they are evolving, so they are system operators now, have to deal with several constraints. And voltage and thermal limits are among the most prominent problems that they have to deal with. And this is because we have an issue with the capacity to support the power flows on our wires. So in simple terms, if you have a wire, you can transfer a limited amount of current on it before it starts melting. So if we all have electric vehicles charging at the same time at home, we might end up demanding too much from the network and the network not coping with it. And the distribution system operators have to find solutions in order to overcome this while maintaining the supply because they are required to give us security of supply. So we have to have a very high reliability of supply. Now, another problem are the distributed generation sources, which can give us the current, but in the opposite direction, but they still create the bottlenecks that can appear when electricity flows downstream. And another issue that I want to mention is the fact that distribution system operators do not currently have visibility of their assets in real time, or of the networks in real time. So they have to manage the networks while they don't know exactly the full topology of the network, because as it has been so far, if you have a small scale PV panel, for example, on your rooftop, you don't even have to let the distribution system operator know that you are installing it. So they don't know about it. They just have to go with the flow, so to speak, and they have to manage their networks, while they might have at this time some generation coming in from Brunel's PV panels up here, while in half an hour, if it's cloudy, this extra generation into the network will decrease. So it has to be a very fast response to changes in demand and generation in the network. Now, about the voltage, one last thing that I want to mention is what Ahmed mentioned as the duck curve. So now the voltage in the system becomes more dynamic, which means that our distribution system operators have to find ways of dealing with it in an efficient manner. And this is where the efficiency of the distribution system comes in. You have here on this slide one paper that is relevant to this subject, which was published quite recently in the IEEE Journal of Photovoltaics with 2 collaborators. And of course, I will be presenting the current project, which focuses exactly on this problem. Now, if we move on to the control systems, we are seeing that we need to control somehow the voltage and the reactive power and the electric vehicle charging in the network. But in order to do so, we have to create the so-called self-healing network. So what we are trying to achieve is to have some electrical networks which have an embedded intelligence and an embedded control that allows them to reconfigure automatically so that those bottlenecks that I mentioned earlier do not appear or are minimized in real time, and also by minimizing the losses in the network. In the UK and worldwide, this automatic network management or self-healing network concept is being developed quite rapidly in the academia, but quite slowly in practice. We do have some trials in the UK and others across the world, and you have here some of them listed, but it has to be noted that they are not mature technologies. They are at trial level in order to prove the concepts, but we are still way off from achieving true self-healing networks. One paper on this was published by a PhD student of mine who graduated in 2020, and it provides a very detailed overview of all the trials that were implemented in the UK at that time. Again, it's a good read if you are interested in it. When it comes to the subject of renewable energy sources, again, this is intertwined with everything else that I discussed about so far. Reverse power flows and the fact that we have congestions, the voltage level, because they are introducing a voltage source in the network towards the end of the network, towards the edge of the network. But one issue that I haven't mentioned so far is the fact that our energy networks are three-phased. And on each phase, we have different consumers connected, while we are not able to know on which phase we are connecting on. The distribution network operator also cannot see on which phase the extra input from renewable energy sources comes from. And on top of this, you have the stochastic charging of electric vehicles, and that creates an issue in unbalancing our network, meaning that we have different loads on the three phases, which creates several issues, and Mohamed will be more aware of the power quality aspects of this, but I'm not going to go into detail. I wanted to point out the fact that renewable energy is great, but for us, from the power system engineering perspective, they are a nightmare. And of course, we wouldn't be able to discuss about efficiency in distribution networks without touching on the digital part of the energy infrastructure. And here, I want to requote something which says, you cannot manage what you cannot measure. I want to requote it as, you cannot manage what is unknown. And the fact that we don't have the visibility of the network at any given time means that we don't know what we have to manage. And by digitalization, we are trying to measure more of our system and to understand more of what is happening in the system. It's worth mentioning, because it's a topical, it's very topical now, that we still rely on gas in order to cover the very fast peaks of demand. and with the uncertainties in gas pricing, the flexible power grids, so these self-healing networks, may be a way forward. And also, we have to take into account the variability of both generation and consumption. So weather influences our generation, which makes things even more complicated. But if we have digital systems in the network, then we can manage our network based on what we know through digitalization. Now, these were the four deconstructed problems of the main problem of energy efficiency in distribution networks. And in the last 11 years or so, I've been working in different projects, either as PI or COI or PDRA, as I started off. But each of those those projects tried to solve one issue or another of the distribution network efficiency. And I'm not going to go through all of them. I have chosen the most recent one, which is implementing digitalization in Turkish distribution networks to improve energy efficiency. This was awarded in January last year, and has a duration of 2 years. And also, very recently, we were successful for an EPSRC DTN Networks Plus project, where I am the PI and Dr. Chen Xing Lai is the COI. But this hasn't started yet, so I won't be talking about that. About TDX Assist, last week, Professor Taylor discussed it quite in detail. So again, I'm not going to mention it. So implementing digitization in Turkish distribution networks to improve energy efficiency, it's a long name, so we shortened it as DGFN, tries to come up with...
Ioana, you're running out of time. I don't
Yes.
know how long, but I'm just reminding you.
Thank you. Yes, I'm going to just have a very brief overview of this project, and then I will finish. This project tries to increase energy efficiency in a specific network in southeastern Turkey, because that distribution system operator is a project partner. And this is the project team. It consists of a lot of early career researchers, one based in the UK and many of them based in Turkey. I'm not going to go into details for the project structure, but we have 4 work packages. And what I want to mention is that we have real life problems. So the networks of this energy company, distribution energy company that we are working with, deals with or supplies one of the poorest areas of Turkey. And there is a lot of energy theft there. We don't like to call it theft in power systems. We call it non-technological losses. And we haven't found a way yet to model these losses in our models in order to take them into account. But DEDASH are working quite hard to get a model and a snapshot of their system that is accurate in order to manage their assets. What our postdoc did here at Brunel was to propose a new control system for PV panels in order to improve the voltage and reduce the losses in the networks. And again, it's technical, so I'm not going to go into detail about the implementation. But of course, these controllers have to have a way of communicating between each other. And we benchmarked our results by comparing it to an IEEE standard. And we observed that our reactive power is better in terms of requirements for our proposed control method, and also the power losses, the active power losses, decrease with our system. Again, the PDRA, Dr. Fatia Boshadi, is working on this. And with that, I'm going to conclude just by advertising 2 PhD topics that I am currently searching students for. So if you have anybody to recommend, please do. One is through the DTP and one is self-funding, but it links with what Mohamed asked about in the morning, about using end-of-life EV storage for electricity networks. So this is why I also wanted to mention it. So with that, I want to thank you for your attention and apologies for taking maybe longer than allocated.
No, that's okay. Thank you very much, Ioana. It was a very nice presentation, giving us the general picture and also describing one of your projects as well. And about the unpredictable behavior of the power generation that you are experiencing. And I thought I had problems in the buildings because of the unpredictable behavior of people, but now electricity is the same as well. Are there any questions, please?
Just a very brief question, Ioana. Now, if you installed a charger in your home to charge your electric vehicle, if you have one, would the electricity authority or distribution authority sort of know about it?
No, at
No.
the moment, no.
Okay.
Which is a big problem for us.
Yeah, I mean, I thought so, because if they knew, perhaps they could manage the time of charging.
Not now. I mean, at an idealized level, a lot of researchers are working on this subject and trying to control the charging of people, but it's only at modeling level because nobody knows what's happening in real life.
Yeah, can I comment here very quickly, because I have one installed at my home.
Okay.
My wife got the electric vehicle there. The ones they fit it, they do tell, for example, if it's British Gas or something like that, they are aware of it, and it's connected to the internet as well.
Yes, but that's the supplier, not the distribution system operator.
Yeah. So the distribution, and they collect the data, of course, and so on.
Yeah, but it's the supplier, so those are separate entities from the people managing the grid.
Yeah, you're right.
That's the problem.
Great, thank you.
Thank you, Sab. That's very good.
Thank you. Thank you very much, Ioana. And I think we will move now to the next presentation by Simon Roberts. Simon is a visiting professor at the Institute and the Resource Efficient Future Cities Center. And he's going to talk to us, as we can see on the screen, is the service industry really low carbon? Simon.
Okay, can you hear me okay?
Yes, but we don't see the presentation now. Yeah, now it's okay.
You can.
Yeah.
Okay, I'll go to that one there and go to full screen. Yes,
Yeah,
is that
that's
okay?
fine. Yes, that's fine.
So I'm going to talk about the service industry. This morning, Atanas Avanov talked about manufacturing, but another important part of the economy is the service industry. It's got a couple of issues. First of all, services are seen as being virtual, no physical aspect to them. And so from that perspective, they're deemed to be very low carbon compared to manufacturing. And then another issue is, what is the service industry? It's quite a curious phrase. Maybe people think of financial services because it has the word service in it. So I'm going to look at this as a broad issue. And I'll start by using this graphic. The service industry is represented by the circle. All those icons are different services. I'll go into more detail in the next slide, but at the top is retail, and on the left is entertainment. On the right, 3 o'clock, is education. So what we're involved with now is, of course, a university, healthcare, and so on. So there's a large number of services. And treating this as an industry, it has inputs necessary for it to function. A very crucial input is employment. So all of us are employed by the university. That's shown by the left-hand side. On the right-hand side, other aspects of other types of inputs. And you can see the icons. The top one is a sort of filling one. That represents the liquid fuels and gas. So the ones that are direct heating of buildings. And on the whole, the representation of the service industry, its impact tends to be just the fuel consumed on site, the gas. But clearly, service industry is a major use for electricity. Further on down are goods coming in. And then finally, there's the construction of the buildings. And each of these emits CO2, as shown on the right-hand side. And this is what I'm going to use for the definition of the footprint. It's going to say all those inputs necessary on the right needed for each of those components of the service industry to operate, and furthermore, their major employers. What I'm not going to look at is the beneficiaries of the services. And the reason why the service industry is important is not just because of what it provides to us, because it is a major employer. This is a historical graph going from 1990 to 2018, so about the last 30 years for the UK. And on the right now, you can see the detail of each of those components which correspond to the service industry. In essence, it's not manufacturing or agriculture, and there's a huge number there. So at the top, this tends to be the sequence in which it's represented in national accounts, the order of industries. The top one is retail and wholesale, transport and storage, then hospitality is quite a major one. Moving on down, further down, there's education, which we're involved with, and quite a major one is healthcare, the green one towards the bottom. So back in 1990, it was employing 21 million, and up to recently, it's 29 million. That's a huge part of the economy. What's quite interesting about this profile here, and I said that many people immediately think of financial services as being the service industry, but in fact, that green band is pretty narrow, is that most of them are staying in the same proportion. No one is really taking over, though we have digitization and so on, and the internet. It's not causing any particular one of these components to disappear. About the only one really that's picked up substantially over this time period is the healthcare. At the end of the 90s, that really picked up in a number of people employed. So just remember that starting point in 1990 of 21 million. So we've got the same timescale here, but now we're doing a couple of things. First is to compare to other countries, and then to other industries, in particular to manufacturing. So the left-hand axis shows number of curves coming out at 1, and that's taken as unity. So for the UK, the black curve, the unity in 1990 is that 21 million. And now, because that's the index, the black line on the right, which went up to 29 million, is basically a third higher. So on this representation, it's shown as 1.33. And of course, by indexing from that time, that particular point in time, we can make comparisons to other countries. The other countries here are comparable economies of Australia, Germany, Italy, and the States. And what's remarkable is how similar the evolution of all our economies are in increasing the degree of service industry and their employment. The only outlier here is Australia, whose service industry, from one might say as a low base in 1990, is increasing a lot, but the other curves are remarkably close together. Now, to compare manufacturing. So again, we take this 21 million for the UK in 1990, and the black curve at the bottom is at about 0.21. And that means in comparison to the 21 million in the service industry, only about a fifth of that revolved in manufacturing. And then still taken as that reference of 21 million, that has been declining down from about 21% to about 12%. So not only is it declining with respect to that reference in 1990, but the service industry itself has been getting bigger. So, and if you were to reference more recently, then the manufacturing ratio would be even less than 12%. So there is an interest in point to do the manufacturing in that the country comparison divides into two groups. And the green and the red lines are for Italy and Germany. So those are notable manufacturers, and their employment in manufacturing is double that with the rest, which is Australia, the UK, and America. But again, what's of note here is these are also been declining with respect to the values in 1990. So this is not atypical. This is what modern economies, at least developed country economies, are doing. They're shifting over to service industry and employing a very substantial proportion of the working population. Now to move on to the footprint from the service industry. This is, again, the same historical period, looking at all greenhouse gases. In the top band, the very dark blue is the non-CO2, majority are CO2 from the green downwards. And now the thing here is that in the graphic, I showed the footprint of the service industry as represented not only by the burning of fuel, but by electricity, where that comes from, by goods and construction. And when we take that definition, that's what's shown here. It's a very unusual one, and it's part of the novel work that I'm doing with my colleague, Colin Axon. And what you see remarkably is that it's been pretty flat at about 20%, with only a slight decline in recent years. That is not only alarmingly high at 20%, which showing how important it is as a greenhouse gas emitter and not low emission, as many think, but it's been very constant, apart from the decline recently. Another point to take note here is the bands above. So the next one up from the service industry is dwellings. That's received a lot of attention. This definition of dwellings, by the way, is not only the use of fuel and electricity in the home, but also the consuming behavior is the blue one above. So those combined together are what the consumers do. So the dwellings, the buildings themselves, have a lot of attention to try and make them more efficient. Consumption, there's trying to persuade people through their buying power to look at the carbon footprint of their purchases, a lot of attention on transport, passenger freight, and so on. But what isn't looked at is to do with the service industry. And that's another reason for this work to raise up as being as important. In the top line, this is called the production approach, which is a conventional approach, which is only looking at emissions with the fuels within the boundaries of the country. But there's another way called consumption approach. And Atanas this morning, he mentioned the footprint from imports. This is very important. The ways it's talked about is that the production approach represents only within the country, domestic sources alone, and consumption includes what comes from imports. And now this is moving on to our work, where we've got the same historical period on the left-hand side, but then the solid curves are where we have our scenario work going through to the future. So the lower curve is for domestic emissions only, called production, and the points on there show real historical data. Whereas if we then incorporate imports, where we're using the sort of average intensity carbon emissions of an economy, which is what we then assign to all the goods essentially which come in and are necessary for the service industry, this is much higher up. That data doesn't go all the way back to 1990. What we're doing here in our scenarios is which is with existing measures, a sort of business as usual, counterfactual. And you can see that there's been a very good trend for the production on the lower one, which is at about 180 on the left million tons of CO2 per year, coming down historically, and we can see that carrying on. There's lots of signs that says it's getting better. And again, was just talking about the service industry, but it hits a plateau at 2030, and that's at 50, and that's very stubborn. And clearly the talk is about net zero at 2050. So not only do we run out of capability of reducing, but it's stubbornly high. And this is really terribly important. And given the major employment aspect of the service industry, you can't just turn it off and lose all that employment. That's just that's a no-go one. That would just substantially increase unemployment. And then when we take into account the offshore, which is the goods brought in, that doubles it up. And with existing measures, they flatten out. So these are huge, huge problems where we're all trying to achieve net zero by 2050. Let's break it down then within our modeling. How do we consider all these components, which in the previous slide showed it all adding up? And this now is taken the consumption approach with imports, and we work on through the colors. So the top one is the blue. On the right, you can see that's fuel. And this basically is to do with gas heating of buildings. So with existing measures, business as usual, is that there's not really reduced very much, where there isn't a really strong incentive to improve the thermal efficiency of buildings. The second one down is electricity. This is red, and it dwindles to nothing in 2030. And what this is meaning is that once you've made renewable or zero fossil energy impact to electricity, substantial renewables and so on, then they're out of the equation. And clearly that's highly beneficial, but there's a lot of residual here, isn't there? The grey ones, dark greys for domestic goods, and this is where we assign a footprint, and then it goes back to Atanas's talk, which was to do with manufacturing, its own contribution. And this is where the service industry needs the goods for it to operate. And there's a footprint not only from domestic, which flattens out, but there's a substantial one for imported goods. Then finally, the bottom four colours, the orange down to the very bottom, on the right-hand side in the key, it says CF, that stands for capital formation, where capital is meant buildings. So we have to look to construction and replacement of buildings, and these are very substantial. So about a third of the emissions from 2030 on is of the buildings themselves. And so you can't simply talk about the running costs. There's no doubt that the service industry is highly dependent on being buildings. And I think I've noticed from the visuals that many people are in their offices. Now, one little bit of insight is to how our modeling method works. You can see we break it down in all sorts of inputs, all sorts of industries. What we're basically doing is within our system, complicated diagram, is to look at inputs and outputs. So let's take a very simple one, not on this graph, but let's suppose we think about a power station. Output is electricity and input is, say, gas. And we take a ratio of the gas needed for the output, which is called efficiency. And we're doing the same thing at all the transitions from goods coming to country, goods and their emissions, and how many goods are needed. What this graph is showing is how many goods are needed per unit of output. Now, this is a bit difficult concept for an engineering department. What we're going to is national accounts, gross value added, those terms. And so we can take the number, which is the output of the service industry as value essentially, and the value of the goods needed per unit of output. But essentially, we're thinking the same concept as if we're looking at the power station and how much gas or other fuel is needed to get the output. This here then has the historical period on the left with real data, and then what we do on the right for the future scenario. So what we're seeing here is that 1990, there are a lot of goods needed in the whole sort of range of whatever they are, which have been declining clearly, but then within the 2000s, they settled out and they seem to be flat. So for the moment, we don't try and pick it apart. We go, well, that is suggesting is going to be constant. So with our phrase for the scenario with existing measures, we extrapolate it with the black line horizontally going forward. What we've then done in our work is to pick apart the use of individual goods, whether that's food, electronics, or whatever, and to see what work is being done. So having done that and how all the goods break down, we then find that with existing solutions, there can be a reduction of about a third, which are the two red lines. And because these are goods used to provide services, this is dematerialization. That's the phrase, isn't it? Taking away the materials necessary for doing services. And in addition, what we've looked at is two rates of transition, a really rapid one, a logistic curve, the S-curve, or a slow one. So we've taken this approach, first of all, to look at all the transitions like the energy intensity of goods and so on, and then to look at what measures are in place to reduce the emissions or change their density, whatever. So here, this shows results of our analysis.
Again, for fairness, your time is coming up. I can see that you've got only 3 more slides, but yeah.
Okay, so here it shows basically the curves don't go to zero with our work. And the summary then is that service industry drives GDP and employment. It's responsible for a lot of emissions. Here's an example of some of the inputs of goods, electronic, pharmaceutical materials, and machinery. They're increasing. Very few measures to date. And we think this is a major problem which will undermine the targets for net zero emissions by 2050. And to finish with, here's some work with my colleagues and some recent papers if you want to follow this further. Thank you very much.
Oh, thank you very much. Sorry to rush you a little bit towards the end, but yeah. Are there any questions, please, for Simon? Simon, I have a question about the recent decline in the service industry. You showed us in the graph that there was a sharp decline for domestic buildings and everything, and you explained it. But what happened to the service industry? You said it is about 20%, but then recently it's coming down a little bit.
Well, the number of measures that are taking place within, so I tell you, when you're talking about decline, you're talking about the emissions?
Yes.
Okay, so clearly one of those is electricity. And there's a strong move by many institutions, I'm sure at Brunel, at least, to shift over to low carbon electricity. That's an easy one. There's another one of dematerialization. So clearly, if you are using less paper, if you're producing less waste food, and as Atanas said this morning, this lean approach is applied to everywhere, because on the whole, this also saves money. It's a win-win. So lots of things are taking place there, but they're really kind of nibbling at the edges.
Yes.
You could knock off about 10 or 20%. And I think the problem we see is when you hit the hard core, as it were, you can't take away various things, and it's very, very difficult to carry on reducing further. So it's the low-hanging fruit, the easy ones we can see have still got a little way to go.
Okay, thank you. Yeah. So it needs to have a similar approach as for the residential building stock in order to have a more rapid decrease of the CO2 emissions. I see another question by Tang, please.
Thank you, Maria. Thank you, Simon, for this interesting talk. So about the modeling, just a question. So I understand there's a lot of like a national or even regional studies or models available, like the Markle model, which has been used in the last decades to examine the energy commodity, emission, creation, etc. So just wondering, are those models appropriate for this kind of analysis which you're working on at the moment?
This analysis is complementary. It does a different thing entirely. Those ones, the Markov one is a market one, which if you can set a price and if you can look at the elasticity of demand for a given change in price, then you can make some projections. What we're looking at here, though, is a systems analysis which says we start with the capital stock of buildings and power stations and other things, and how much comes out of those. If we need to have more services, we need to have more buildings. It's as sort of simple as that. If we need more power, we need more wind turbines and so on. And this is quite a good one that sense checks, and there's a huge amount of data in national accounts, there's other IEA data and so on, which we can bring together, which has a sort of sense check to what's actually possible. So it's complementary to Markov, but I think it's one that's not being taken note of, and there's a huge amount of realism looking forward. The most crucial thing is there are no dark corners here. Everything is looked at. If you take all of national accounts, it examines every part of the economy, services, and so on, and thus you can see in our analysis. If you need to maintain jobs, yes, we do. Then you have to have the service industry and you have to have its footprint. Duh. It's a very simple idea, and it just follows through from looking at the data. So I think it's quite an important process in complement to the others.
Okay, thank you, Simon.
Thank you. Are they, Savas? Yeah, you had.
Yeah, Simon, thanks very much for the presentation. Very interesting. I mean, my question is that really following your projections, then we're going to hit a flat sort of a plateau that really is very difficult to go beyond that. And but do you have any suggestions of how do we handle that, or how the government handles that?
I think in all the areas where the problems are seen, it takes first of all a matter of recognition, then decide that it's necessary to do, and then to put the effort into what are the measures. And as we've had all the talks earlier today, looking at the injection of renewables, distributed generation, PV on homes and electric vehicles, this is energizing all the research and looking for solutions, the self-healing and so on. So we need to recognize, make it important, and then do the necessary steps. And I think the major problem is that we're so far short of that. And the economist's view is to try and monetize carbon. And if you monetize carbon, for instance, into people's buying power, and if they see they have to do only things that have low carbon, the natural consequence is they're going to grind down the economy. But the buyers can't make those choices not to do various things. It needs a more systemic approach and a more individual looking at the particular industry. We've seen since the COVID and lockdown, the hospitality industry is called an industry, has seemed to be terribly important, and the need to get it going because of all the employment and other sorts of benefits. So you have to look in details, what does the hospitality industry need? Are they wasting lots of food for so on, things like that? And that needs its own attention to see the benefit. I think it needs the imagination and the resources to be put in to make sure that we continue the trend downwards and don't plateau at 2030.
Yeah, great, thank you.
Okay. Thank you. Unless there is any other pressing question, I think we need to move on. So thank you very much, Simon, for your time and the insights on the general picture. Thank you. The next presentation, we are moving now to the materials of all these buildings that they need to be done for the service industry and others. So the next presentation will be by Seyed Ghaffar, and he's going to talk about digital fabrication of low carbon cementitious building blocks. And Seyed is here ready with his presentation. Thank you.
Thank you very much, Maria, and good afternoon, everyone. So I will be talking about the construction industry, which is in a way related to what we were discussing the whole day. And the focus is on material science and how we can drive down the CO2 emissions. I would like to start by emphasizing again that my research is focused on delivering the 17 Sustainable Development Goals in a hope to transform our world by 2030. Specifically, I am focused on goal number 11, sustainable cities and communities, and goal number 12, which is responsible consumption and production. The name of my research group or research team is Additive Manufacturing Technology and Construction. And what we do is basically combining different fields of sciences together in a multidisciplinary approach to deliver innovation and transformation of the construction industry. The focus is on material science, design formulations, and by that I mean processed organic and inorganic waste, plus the additives, the smart materials that can change a certain property in concrete. And the main science is the design formulation. It's similar to kind of, cooking. When you are cooking and when you add different ingredients and then you have an output, this is what we do with the material science, and we try to optimize a certain performance, either mechanical, physical, durability, and so on. And hopefully by the end of this optimized design formulation, we will have a printable feedstock, just similar to the cement bags that we see on sites and construction sites. But the difference is this is low carbon and also is suitable for the application of 3D printing. So that really fits well with the some of the advantages of 3D printing. When it comes to concrete 3D printing, we have advantages such as reduction in material waste and labor. We have a fully automated production, improved construction speed, of course, and with there is no need for molds or form work, which that means it will reduce the environmental footprint and also allow the freedom of shape that architects for so many years have desired. Of course, with the traditional concrete casting, the molds or the formworks have a certain shape, either rectangular or circular. And then after the concrete is casted and cured for 24 hours, the mold is no longer used, and that is called a waste. But with 3D printing application, with 3D printing technology, we know we don't need any molds, so therefore we are reducing the waste generated in the construction industry, and also we allow some freedom for futuristic geometries to be realized and to be printed. So what is digital fabrication? Digital fabrication for me has three important elements that should work together in a gear format to drive forward the technology. One of them is the printer itself, either a robotic 3D printing, a simple robotic arm that is capable of doing any applications needed. The environment that the robot is in, because the material is quite sensitive, the construction concrete material is quite difficult to optimize and work with. The environment, the moisture, the temperature can have an influence on the end properties. So it is quite important where the printer is and how the printer is operated. The system size, the robot speed and movement, the nozzle geometry, the mechanical adaptation. So this is one element of the digital fabrication. The other element is the geometry, the filaments, the overall shape, the 3D curvatures that we can achieve with 3D printing technology, the reinforcement, the strength and stiffness. But most important element, I'm not just saying that because my background is material engineering, but I think printable feedstock and printable material are the most and the biggest element in the technology. So the composition of this material with the use of low environmental impact materials, with the use of alternatives to Portland cement, we can have a much more sustainable delivery of this technology. The composition is important, the mixed design formulation, the aggregate size that we put in order to develop that concrete. sort of the improving the compatibility, the admixtures that we use, and so on. This is the most important element when it comes to digital fabrication. And you can read more about the all these in the publication that we had in 2018. So the focus of my research group is on 3D printing of low carbon cementitious composites. So we are using zero Portland cement, which is one of the main binders in concrete. And we are using a material which is called geopolymer or alkali activated materials. And this is some of the prints that we have done in Brunel Labs. And the other focus of our research is on incorporation or replacement of natural aggregates with waste feedstock. So we have picked up 3 different streams. One of them is the recycled PVC from the industry, from the cables. Another one is recycled rubber from the tire and automotive industry. And the other one is recycled brick from the construction industry. And we have tried to replace the natural sand or gravel in the concrete with these waste that otherwise would have gone to landfill. And I wanted to just bring your attention to some of the facts around the concrete and the construction industry. So the concrete is the most used material in the construction sector, reaching approximately 30 billion tons annually. And OPC, or ordinary Portland cement, which is the main binder, the main binder that we use in order to develop the concrete, is responsible for 6 to 9% of the global GHG emissions, and that is equivalent to the aviation industry. So the modern society focuses on faces urgent environmental challenges. We've talked about CO2 emissions quite a lot. The waste landfilling is another one that is quite important to us, especially the construction sector. And another important element which is very, very relevant to the construction sector is the depletion of raw materials that we've been using for centuries in order to develop the society and infrastructure. So the government has identified the construction industry as one of the key sectors where there is a need for a change in order to reach circular economy and sustainable development. So these are my motivation in order to deliver on a research where we can say we have a sustainable construction industry. So the geopolymers that we are focusing on, or alkaline activated materials, they are much more sustainable compared to OPC. And there has been plenty of studies conducting LCAs on these materials, and the environmental benefit is in a very wide range. Some research groups range them from 9% to 45%, and a more recent study has shown the capability of geopolymer to reduce the GHGs by around 80%, which is quite encouraging. My group has not done any work on the LCA, so I cannot really judge on that, but obviously LCA, whatever you input, the output is according to your input. So you really have to study and take these numbers and these statistics with a pinch of salt and really understand what has gone into the computation of these numbers. And within the geopolymer field, we are focusing on a more advanced geopolymer, so geopolymer 2.0, which eliminates the use of chemical agents in liquid form. And that is good because these chemical agents in a liquid form, they could be really hazardous to handle on site, and they could be very corrosive, and they have other environmental impacts, which doesn't put them into that good position that we wanted when you compare it to OPC. So now we are focusing on 1 part geopolymer, or just add water mixes, which means the chemical agent that we call activator is in the form of a powder. And we are focusing on byproducts that are coming from the coal burning industry and the steel manufacturing industry, namely the fly ash and the GGBS, or slag, as it's widely known. So the transformation of the construction industry, we are lacking behind, decades behind our neighboring industries, such as automotive, biomedical. And we need to introduce automation and digital technologies to the construction processes. The focus should be on valorizing construction and demolition waste, which is one of the huge challenges faced by the industry, and try to use material science in order to optimize a certain performance and incorporate these wastes into construction materials and construction products. So one of the current projects that was funded by Horizon 2020, and we postponed it by 10 months, so it began January 2022, is called Digital Fabrication and Integration of Material Reuse. We call it DigiMat in short acronym, and this is our consortium. We have partners, few partners from Europe that are helping on this project. Some of the preliminary results, and it's very important to show you how we started. We started with a mortar gun, and this is the hopper system. This is where we put the materials, and we wanted to see if they are extrudable. But then slowly back in 2017, with a small funding that I was able to get from the university, I purchased this gantry system 3D printer, and now we have updated and upgraded this 3D printer. Last summer we done some upgrades, which means we can print a lot larger size, but this is 0.5 meter by 0.5 meter by 30 centimeters in the Z axis, but now that 30 centimeter is updated to 1 meter. And this is how we started back in 2017, but now we can really print really large structures. Here there is a video of one of our first initial prints using the Portland cement binder system, which is not very sustainable, but is a benchmarking is for benchmarking against our new materials, which are a lot more sustainable. And you can see the final prints and the complexity that we can have with concrete 3D printing, such as the twisted column here and so on. But I want you to look at the resolution and the print layers and the print quality here. When we can compare it to our new material in the next slide, you can see that we've achieved a lot more improved properties when it comes to shape stability, when it comes to shape retention, and the whole resolution of the printing. And this is thanks to our geopolymers that we are using. Not only they are more sustainable compared to Portland cement, but they are more suitable for 3D printing application, and they actually result in a much better and much better results in terms of resolution and the print quality. And this is a video showing our geopolymer, which is using recycled sand and recycled waste brick. So the clay bricks that we have used here have been crushed into small sizes, and they replace the natural sand, which we are running out of, with these waste bricks. So our studies, this is just one of the tables that I wanted to focus on. We've used these type of low carbon binders, fly ash and GGBS and silica fume. We use chemical agents to activate them, and we use some polyvinyl alcohol fibers and attapulgite nanoclay. These are the smart admixtures that I initially stated, and they are the admixtures that help us to get and optimize a certain performance. And here is our framework of the tests and the study that we conducted. We use these two important materials to help us in order to increase the flexural strength, the 3-point bending test, attapulgite and PVA fibers. We studied the fresh properties, so as concrete is mixed, immediately after mixing. We also did some casting of the composite in order to have a benchmark. And of course, we 3D printed the samples. We investigated the mechanical strength and the microstructure in order to be able to draw some conclusions. The mechanical results were very encouraging. We were able to get flexural strength of near 14 MPa after 7 days, which is quite high compared to Portland cement. Portland cement after 7 days, you can only get half of this. And compressive strength, which is one of the most important parameters when you talk about building blocks, we were able to get as high as 70 MPa, which when you compare that to Portland cement, you can only get around 50 MPa, depending on the cement type and category that you're using. But also you have to bear in mind that these binders have very minimum environmental impact compared to OPC. We looked at the microstructure. The SEM images here are showing us the PVA fiber and the interface of the cement of the binder, low carbon binders and the fibers, and how the cracks have been arrested or blocked because of the presence of these fibers. So this is why the flexural strength is as high as it is, and as high as I showed you in the previous slide. So in the future, we want to continue to develop 3D printable construction materials for sustainable manufacturing. Really and truly enable circularity in the built environment through material science, property engineering, and innovative technologies such as 3D printing. And base valorization is an important element of my research, and we want to integrate as much as we can into construction materials and hopefully reduce the CO2 impact of concrete components by 70%. So the key takeaway message for my presentation is that creative ideas are needed to reduce the waste stream from the construction sector, save the Earth's natural resources, and hopefully be able to deliver net zero construction, net zero carbon construction. So I want to give my thanks to my research team, my research fellows, and the external funds that have enabled me to carry out these research. Some of my MSc students are also acknowledged for their work and their contribution to the research. Thank you very much for your attention.
Thank you. Perfect timing. My timing just started ringing. Thank you very much, Seyed, about this very, very important presentation to explain to us and the details of your research. Are there any questions, please? Savas?
Yeah, Seyed, a very, very interesting work. Thanks very much for the excellent presentation. I mean, my question is a bit general, really, out of curiosity. I mean, there is a move really for, particularly for domestic dwellings, to go towards steel construction with a lot of insulation. Is that, I mean, how do you compare really the sort of concrete as opposed to steel these days in terms of speed of construction, in terms of, I know you said that you don't do in the group LCA, but I don't know whether you had a view really about comparison in terms of life cycle sort of analysis. Or...
Yeah, thank you very much, Savas, for the question. So, I mean, there are plenty of projects, and we need to use both steel and concrete, and we can never reduce the usage of concrete in this industry. So there will be plenty of applications for concrete. So why not make that concrete lower carbon by replacing this Portland cement, which is the main ingredient in concrete? And another approach that we are using is to remove all these natural resources that we are extracting, extracting from the Earth's resources, and incorporate some waste. But compared to steel and steel manufacturing and steel construction, of course, they are a lot more easier to construct. The construction speed is relatively higher compared to traditional concrete. In terms of LCA, I know there is also a lot of move in the steel industry to use alternative energy sources for their production, for their manufacturing. So their LCA and their argument is also that they are moving the industry towards lower carbon emissions, but is not something that I have full knowledge of.
No, but I think the shapes that you showed there are very interesting in terms of probably still a bit very difficult to get a similar sort of.
Absolutely. I mean, for years, civil engineers for years have been struggling with the demands of architects, and they throw these creative images and objects, and they want civil engineers to realize them. But obviously, the technology back then didn't allow the civil engineers to respond and address the requests of architects. But now I think with the 3D printing technology, slowly, obviously, the feasibility and upscaling is still a big question, and there's a lot of work to be done in order to make this an industrial scale success.
Great, thanks very much.
Yeah.
You're welcome.
Actually, I have a general question as well. Seyed, you talk about the recycling of materials from the construction industry in your work. Have you looked or have you ever used materials from automotive industry, specifically end-of-life vehicles, for example? Are they useful in your research or?
Yeah, I mean, the automotive industry, I mean, the car industry, no, but the tires from the cars, especially the heavy vehicles, they contain steel, and we have worked with a company called Zero Waste Works, which is a small SME based in Sheffield. They recycled steel fibers from these huge lorry tires, But unfortunately, it didn't work. We did some preliminary results, and the interfacial bonding between this steel and the surrounding concrete wasn't strong enough.
Okay.
So it didn't really improve any of the properties, because at the end of the day, we want that structural robustness from our products, from our concrete building blocks. And unfortunately, with the incorporation of these waste steel fibers from heavy lorry tires, we were not able to achieve that.
Yeah.
In terms of other materials from the automotive industry, no, we haven't tried anything.
You haven't looked into, yeah. Okay, thank you. Any other questions, please? It seems not. So thank you very much for your presentation. And yeah, we'll come back to you again. Very, very interesting line of research. Thank you.
Thank you.
So we're now moving to the next presentation by Kangkang Tang, who is going to talk to us on a very topical area about design of hospitals, and in particular designing hospital digital twins for health services. So we have your presentation. Okay, thank you. It's
Thank you very much, Maria. Yeah, thank you. Yeah, my name is Kangkang Tang. I'm a civil engineer, and I would like to talk about what else we can help with the building design in civil engineering, in addition to the to design a more energy efficient structure, and also how to bring down the CO2, which is about to design these more resilient healthcare services through the development of digital twins. So there have already a lot of definition about resilience, and in the context of building design. But my interpretation is that resilience is more than just being prepared for another hurricane, a superstorm, another pandemic. It also includes the ability to anticipate such future uncertainties and challenges without compromising its present safety and efficiencies. So during the first wave of COVID-19, people were more likely to catch this disease in the care home and in the NHS hospital, as a matter of fact. So local hospital has to close down their majority of their facilities due to this serious community transmission of the disease. So this happened during the first wave back in 2020. And similar issues actually took place almost 200 years ago during the Crimean War, 1853. So in the winter of 1854, over 4,000 soldiers died at the battlefield hospital, and the majority of these deaths were due to infectious disease rather than these battlefield casualties. So this also led to a major research collaboration between Nightingale, the pioneer in nursing, and Brunel, and the design of this new battlefield hospital, Rankill Hospital, which was prefabricated and shipped to Seyed, over 2,000 miles away from home, from the UK, by the way. So Brunel's design was based on this prefabricated wooden structure. So just try to see if this laser pen works or not. So this is like a standard module. Each of these consists of 2 walls. Each wall has got 25 beds. So they have this shared sanitary areas such as toilet, water closet. So this module was repeated. It's in the other word, is extendable to reach a capacity to treat over 1,000 patients. And this yield a death rate which is 90% lower than the hospital where Nightingale worked at. So this also set a new standard for ventilation, hygiene access, and hospital design and construction. So I think this very hospital design represents the spirit of resilience. And bear in mind that Brunel completed this design in just 6 working days. I guess he doesn't have any annual leave at all. So, but this was like nearly 2 centuries again in 1855. So I wish to say this is a kind of the spirit of resilience we are talking about, we wish to achieve. It is quite remarkable that after nearly 2 centuries, Nightingale's and Brunel's design principles are still valid nowadays. We can see these similar concerns in the layout of this London XL Nightingale Hospital back in 2020. We can see these similar pavilion style hospitals, and we can see these high ceilings to promote ventilations, which is of course enhanced by mechanical ventilations. So what we can do in civil engineering, we aim to discuss the vision about the future resilient hospital design through the development of these healthcare digital twins. So this picture just shows the principles, a concept. So the purpose for this particular digital twin is to better prevent and to control these hospital-acquired infections through this more resilient building design. A digital twin is basically a digital representation of a physical asset, such as a building, a physical object, and even a medical process. So using this digital counterpart, which is showing on the upside of this picture, so we can model a very sophisticated future crisis, such as another pandemic. And in the context of health and care. So this virtual model allows us to make the judgment on which is the best building design, building layout to better prevent such cross infections. I will talk about later how to judge which one is better in terms of this the prevention of these cross infections. So this is achieved through this agent-based modeling, which I'm going to talk about in the next slide. So this, in this mirror world or in these digital twins, we can make the judgment on which design layout is the best option to prevent certain future crises, and which will be reflected into our nowadays design. We can make this decision and affect our design nowadays. So this shows a visualized result through this agent-based modeling. So this patient in red represents the COVID patient, and the others in pink, this shows those who are likely to be infected by COVID because they stay in the same room with these index patients. So this epidemiological analysis was based on this infection model or this Wells and Rayleigh model, which was embedded into this agent-based modeling simulations. So we can predict the risk of nosocomial infection of this transmissible disease of COVID-19, and even make the prediction for the R factors. In this particular model, which just present a small corner of this hospital, which we try to model like with nearly 200 patients, the risk of nosocomial infection was about 8.2%. Okay, so this is the digital hospital I have created. And the previous slide just to show the result, visualize the result in one of the corners. So this digital hospital was created using this building information modeling software, and later allows this agent-based modeling and this infection model analysis to be conducted. As you can see, this original building design, this adopts a two-way systems for both the patients and the staffs. So I used the similar method to create other departments running by the hospital, including the A&E and UTCs. In addition to this infection risk analysis, some other useful information can be obtained through these computer simulations, such as this big analysis, how congested this common area, this concourse is going to be through this agent-based modeling. And also we can analyze how this social distance requirement can be satisfied. So this modeling result shows that based on this 2-meter social distancing requirement, how good, how bad this can be met. By the way, these results are discussed in this paper shown below, published last year. So this is on page slide 10. So I'm talking about how we can help as a civil engineer. So previously, just show through this digital hospital, what we can do about it. And next is how we civil engineer can help with the hospital developers to better control these infectious disease transmissions. So this shows the development of these two-way systems based on the existing building layout, but we can provide extra separations by changing the building layout by using these lightweight partitions. So this gives these separate pathways for both patients and the staff and the medical staffs to check in and check out. So I run the similar model as the previous one, and this time we can bring down the infection rate from, I think the previous one was 8.2%, and this one can reduce down to 6.1%. And similarly, we can investigate how congested the corridor is going to be. By the way, we introduced another pathways to achieve this two-way system. So we now have two concourses in this building model. And also we can see how good, how bad we can help with these social distance requirements by reducing the total number of patients and staffs per meter squared or per 2 meters squared. So this improved building layout will help to maintain this adequate social distancing requirement of patients and staffs. So this was one of the previous slide when I showed this digital twin concept. We can justify the resilience of a building design based on its ability to prevent a nosocomial infection, because this digital twin I'm talking about is in particular, it is to prevent, to control the nosocomial infection. So this is our major purpose for this project for the time being. So in addition, we can build this hospital to be more versatile or to have the ability to change the layout without costing too much. So this can be achieved through this modern method of construction or MMC, or like my colleague Seyed mentioned, through this 3D print, we can bring down the cost. So this, we can achieve this more versatile building layout without costing too much. So this is the last slide. This is an ongoing project, and it's collaborating with our computer science department and the UK major healthcare developer and the local hospitals. And thank you very much.
Thank you. Thank you, Tang. Very, very nice. And as I said in the beginning, very topical presentation for hospitals, but I suppose it can apply to other buildings as well as you extend the method. I think we have a question from Angus. Gus?
Yeah, thanks. Thanks very much, Maria. Yeah, lovely talk. Excuse my ignorance of this question, but what is the difference between a digital twin and a computer model, or what would have been called a computer model in the past? What do digital twins do that what we would have called computer models don't?
Well, I think it was called a computer model, a digital model in the past. A digital twin, my understanding is you can put different layers of salt on top of it, such as we can use this digital twin for one project to calculate the CO2, the energy efficiency. And for this, we can put a different layer. We can consider the different priorities, such as for hospital to control the infections. So to be honest, I think the bottom line is there's no too much difference.
Yes, in a lot of projects there is not a lot of difference. In some projects as well, there is a connection with a physical building in terms of sensors, but I have never seen it used too much as well. So, yeah, thank you. And I think there is a question from Savas.
Yeah, Kangkang, thanks very much for the interesting presentation. I mean, I wanted to ask really a bit more detail about the type of modeling you've done, whether you based it on existing building models or whether it's something which is completely new.
Yeah, I created this building model from scratch. So which is try to simulate, this local hospital, but in a simplified way. So I created a building model. I run this agent-based modeling, which is basically to simulate patients and medical staffs as individual agents. And on top of this, I superimposed this infection model because I wish to find out if with one index patient of COVID or with a few of them, how bad, how good my building can prevent this cross-infection happening. So I need to work this out. So I need something else, this infection model to be superimposed. So this model have a few layers of data. Thank you.
How does it compare with, for example, there are models simulating fires in buildings, and then how the sort of occupants behave or should behave really during fire? Is that,
yeah, I think that's a good question. I think this certainly can be used to model something like you mentioned, the fire evacuation event. How quick, how bad the people can be evacuated. This, by the way, is required by the UK building regulations, and such as for the structural engineer, for the civil engineers, we need to design this building, to allow the people, such as our lecture theaters, to allow the students to be evacuated timely. So this can be used for that purpose to check how efficient we can achieve this purpose. Yes.
Okay, and then what is the next step for the research?
Yeah, next step, we wish to keep working on this. And as I mentioned, we are creating some typical UK hospital models, which is something like the local hospital, the city hospital, which is a big tower sitting on the slab. The slab is mainly, for these consultations. And these walls are mainly in these towers, and also so for some low-rise hospitals which are away from the city. And another typical one is what we call the street hospital, such as those old hospitals. They are evolving from the very old hospitals. So this typical one, they have a totally different priorities. And we wish to create these different digital twins, and we can work out the best building layout, which can be most suitable for their future needs. So yeah, that's one reason we need to work with the hospitals. Yeah.
Yeah, great. Thank you very much.
Thank you.
Thank you. Any other questions? Okay, thank you very much, Kangkang. And also, I know that you had organized an international online workshop in the summer, that there were quite a lot of ideas discussed, and possibly a kind of consortium is being built on that one, which would be very, very nice.
Thank you very much.
So our last presentation today is by Harjit Singh, who will continue the theme for buildings, not for hospitals, and he's going to talk about solar energy and vacuum insulation for buildings to improve their energy efficiency. So thank you, Harjit.
Thank you very much, Maria, and hopefully everyone can hear me. And I apologize for standing between you and your tea, but shouldn't be very long, I hope. So what we have is, I'm going to talk about concentrating solar and vacuum insulation, especially for buildings. Uh, just to start with, I just want to mention that our research has been funded by a variety of funders listed here and several others as well. And I'm really thankful for that, and also to the contributors, which are colleagues from Brunel as well as internationally, and also students and researchers. So to give an idea, but let me just do the pointer, please. So what we're doing is this, that why we're talking about buildings here is, in my opinion, there are three reasons. Number one is this, the buildings are the largest or the highest valued asset class humans have. They've been valued at around the world at 150 trillion euros, which is 20 times more than the gold ever mined. But they are becoming an environmental liability now, because as we know, they're emitting around 30% of the emissions from EU as well as UK. Then finally, also they are becoming difficult to run or maintain for thermal comfortable conditions point of view as well. For example, we know that at this stage, all of us are end users of energy in buildings, and we know that this year the price of the gas has gone up, and we'll be paying 54% more at an average compared to last year. It is because the gas prices have gone up by from 5 pence last year to 7 pence for every kilowatt hour, and electricity from 18 pence kilowatt hour to 28 pence per kilowatt hour. Clearly, there are motivations that we should talk about energy in buildings. And also the trivial matter that we're facing here is this, that the UK is to deliver the net zero target by 2050. This is when the CO2 emissions in 2021 went up by 6.3% against 2020 emissions. So clearly, there is one target, but there are what actually is happening on the ground is totally different. And luckily, it's been identified in the heat and building strategy published by the government that to meet this net zero, we should be bringing all heat in the buildings to completely decarbonized, which is a challenge. Why? Is because number one, it's not a small amount of heat we're talking about. In buildings in the UK, for example, dwellings, we have 29 million dwellings in the UK. They are consuming 75% of their energy in the form of heat at below 80 degrees centigrades. So electricity probably is a solution, but not is the only solution. Then also we have to remember that this heat is not only simply simple heat, but it also is 20% of the carbon dioxide emissions from the UK. So the target is big. So what we're going to do about it is, we've gone about doing a common sensible approach, whereby we're looking into applying the energy efficiency measures, whereby you're using things like improved building fabric, windows, etc., which when applied on a high energy demand building, they can convert them into a low energy demand building. So the residual demand of energy in this case then could be easily met, hopefully, by supply side technological interventions, which are solar, biomass, etc., or even the new technologies, which are heat pumps. Which in concept form, then they convert the building into zero or energy positive buildings. But that's all good and well, but there are challenges. The challenges are this, that which insulation to use, for example, or what kind of solar technologies to use if we are generating energy in this case. So what my research focuses on developing something called vacuum insulation panels to provide solution for insulation for buildings as well as other applications within the built environment. Then also within solar energy, we've looked into developing concentrating photovoltaics and thermal panels. To give an idea that why vacuum insulation panel is important, or why insulation is important, is this: at the end of 2021 in Great Britain, 30% of the dwellings with cavity wall insulation had no insulation in their cavities. 34% lofts were uninsulated. And 91% of the buildings with solid walls were not insulated. They had no insulation at all. So clearly, there is a huge amount of insulation needed to make these dwellings decarbonized, as the government has set the target for. But in my view, these are the ones which have been left out because they are difficult to insulate. And there are a variety of reasons for that. There could be economic and technological reasons. And that's where I believe that the one of the first research that I want to talk about today steps in, which is vacuum insulation panel. Now, vacuum insulation panels for the unchristianed are those are insulation which is a two-part insulation, whereby you have the inner core, which is porous material, and which is vacuumized. As a result of this the vacuum, you can achieve a low level of thermal conductivity. But the challenge then becomes that how to maintain this vacuum over in the context of buildings for 100 years. Of course, there are other challenges within it, which are listed in our publications shown here. But then the benefit of, if you can maintain the vacuum and if you can maintain the structure of the VIPs over 100 years, let's say, is this, that the thermal conductivity of these systems is as low as 2 milliwatt per meter Kelvin, which is 20 times lower than any existing insulation. And one of the insulation that we've developed, for example, in our own lab is shown here, which is a rectangular insulation, 150 millimeter by 150 millimeter. But of course, it can be produced in larger quantities and larger sizes as well. So because of this low thermal conductivity, the benefit is that you can use very thin layers of it to produce the similar amount of U value that will be produced by larger insulation thickness layers. The example is shown here. For example, if you want to convert a 0.53 watt per meter square Kelvin U value, a typical UK dwelling wall, to a low U value, let's say 0.15 U value wall, then a VIP of about 35 millimeter thickness will be sufficient compared to about 100 millimeters thickness of phenolic foam and about 175 millimeter thickness of glass fiber required. So there is a benefit, and that's why the idea is that I was saying that the buildings which are difficult to insulate, which have been left to be insulated, is this, that a lot of them are narrow buildings, very narrow buildings. They are in the inner cities, and there also some of them are listed as well. If that's the case, these buildings will require very narrow thickness layers of insulation and still able to meet the energy efficiency standards of as the desires are. So in this case, vacuum insulation panel is a way forward. We've done a lot of simulations and a lot of work on various research projects in Brunel. So what we've done is this, that lately we're now simulating various buildings within the UK and Europe, funded by industrial conglomerate based in Europe. Is this, that we're trying to do, we're trying to see how much energy could be saved by introducing vacuum insulation panels in buildings. And in this case, I'm showing the result for a typical semi-detached building, a 3-bedroom semi-detached building based in London, whereby the heat energy of the yearly demand of heat energy from nearly 28,000 kilowatt hours could be reduced down to 5,496 kilowatt hour by using vacuum insulation panels. But of course, it's not all that easy. Is because the developing vacuum insulation panels, as well as then predicting their long-term performance, is a very complex phenomena, whereby we've been involved in a few years, and we developed our own computer models, as well as the very extensive lab as well at Brunel. But we're progressing towards it. And also through this research, we've shown that how VIPs not only could be used to improve the building fabric, but could also be used within the building and built environment for other applications, such as for refrigerators, ovens, dishwashers, washing machines, as well as even the cold storage. The reason for that would be this, that we're selling around the world a huge amount of refrigerators and freezers every year. The example is within only European Union and North America, there's 17 million fridges and 2.5 million freezers sold every year. And they are responsible for a huge amount of emissions, depending on which source of power they are using. And in this case, we've shown through our research that 60% of the cooling load is transmitted through the walls, which can be saved, which then, if insulated by VIPs, could save, number one, the CO2 emissions because by reducing the energy demand by greater than 50%, and also at the same time by introducing the more insulating or more thermally resistant insulation in the form of VIPs, we could save space as well, or make rather space within the refrigerated compartments, allowing the freezers to be more attractive to the customers. The example here is this: that a normal fridge has walls up to about 60 millimeter thick, because the insulation inside is very thick. But we've shown that only a 12 millimeter thick VIP could bring down the U value of the wall from 1.3 watt per meter square to only 0.3. So clearly, a huge amount of space could be saved within the refrigerated compartment by using it in systems like VIPs. We're currently working on a grant, which is about 750K US dollars, for developing vacuum insulation panels for a variety of applications within the built environment. We've also shown their use into cold storage in Kenya. And also we've developed in the past a vaccine storage device for Bill and Melinda Gates Foundation by using VIPs. The target here was to maintain the vaccine at temperatures of 2 to 8 degrees centigrade for about 40 days, when it's used in places like in Zambia or on deeper Africa, where the power is not that easily available. Plenty of publications in the area. Some of them are listed here, and we're welcome to read them, please. Now, on the solar photovoltaic sides, or the solar generation side, I want to talk to you about photovoltaics. The photovoltaics look like this. Some of us who know them, they would have seen them in roofs. But I'm sure people have objection to this image because it doesn't show it in a very good light. These photovoltaic panels. But the thing is, the challenge is this year. The UK wants to install 12 gigawatt of domestic rooftop by 2030, whereas the current capacity stands at 3.3 gigawatt. When we are installing only 0.2 gigawatt per year, and my calculations are that we need minimum 1.1 gigawatt per year installed on rooftops to meet the target of 2030. And clearly we are not meeting it. So what could be done about this? But what I think is this, that what the reasons that why we're not meeting this, or why the growth is slow, is this: number one, there is less incentive for people to go to photovoltaics because there is a very easy availability of grid electricity. Secondly, a very practical reason is this, that there is limited amount of roof space available in the houses in the UK, because, for example, for a 4 kilowatt system, you require about 11 meters square of south-facing unshaded roof space. Not many houses will have it. Finally, you have the capacity of the panels, which cannot produce, number one, power when they are exposed to diffuse radiation, as well as they are limited in their capacity to produce simultaneously heat and power or cooling. So that means there is not additional advantage or value added to them. And towards this, what we have done is then we've been developing here systems which we call low concentrating photovoltaic systems and photovoltaic thermal systems, which one example is which we recently developed on the Recoast project. It's a European Union funded project. Now on this one, we developed 3 types of concentrators, which are compound parabolic VTRF and asymmetric compound parabolic concentrators, and showed their performance in conjunction with the conventional silicon cells for producing power up to 40% more than a flat PV panel in London. The installations were done in London, in Brunel. You're welcome to see it in the Clifton building in the student halls, as well as in VV in Switzerland. The idea was that here not only we show more power produced, but also we wanted to demonstrate the multifunctionality. We measured the performance over 16 months minimum, and we've done publications. Very important publications have come. 2 of them have actually several have come from this work, but 2 are listed here. But then also there are more to come as well as we're analyzing the data. On the solar thermal concentrator side, the normal concentrators which produce high temperatures look like this, but these are very big and they cannot be installed on roofs. So the challenge here is then we should be able to develop systems which are able to make use of, number one, diffuse radiation, which is characteristic of radiation in the UK. Up to 55% or more than times in the daytimes in the UK, we get diffuse radiation. So we wanted to achieve higher optical efficiency without any sun tracking, and also are able to we should be able to deliver higher temperatures up to, say, let's say 200 degrees or even higher. Our system has been enabled to achieve so by developing what we have what we would say is a directly absorbing nanofluid, which absorbs solar radiation directly over from the very low, short radiation to the very long wave radiation, as well as then transfers heat to the end user demand center. We've developed these systems on various projects listed here, and also demonstrated their use for, number one, application of energy generation, electricity generation through ORC, organic Rankine cycles in Egypt, for finally for cooling, and also for running a cold storage in Kenya, then also for running a biogas reactor for thermophilic reactions in India. The several publications have come up as well, and my team has tested them here as well as across the world. In summary, I'm not sure how I'm
This
doing.
was my alarm, so you're in good time.
All right. Okay. Okay. Thank you very much. So these are new technologies which we just talked about. There's not much experience of them in buildings in real life, but so there are challenges. We know them, and we're progressing towards resolving them. We have a good track record of attracting funds, and hopefully we'll be continue to do that. And happy to collaborate with colleagues. Thank you very much for attention.
Thank you very much, Harjit. Thank you for outlining two technologies that they could help in reducing the energy consumption in buildings for insulation or for generation of electricity. Very nice, very nice.
Thank you.
Any questions, please?
Still too late, I suppose, in the day.
People are getting a little bit tired as well. But Savas, can I ask one question before I let Savas ask his question? Okay. You talked in the beginning, before you started talking about the technologies, about decarbonization of buildings, which means electrification for heating and cooling. And no, it doesn't?
No,
okay.
I'm not a big supporter of electrification, to be honest, if I have preempted your question.
Yes, but how you can achieve decarbonization then?
Heat should be met, the heat demand should be met by heat generation. This is what I'm saying. Like, I'm not saying in every situation. Of course, in some situations, probably electricity can be converted easily and cheaply in heat, but in other situations, we should rather generate heat, because generating heat is much cheaper, more efficient than generating electricity.
Yes. So heat, but without gas.
Yes,
okay.
heat, but without gas. Yeah. The heat is it has to come from solar or somewhere other sources.
Yes.
That's why I spoke about two technologies: solar PV for electricity and solar thermal for heat generation.
Heat generation. Yeah. Okay. Thank you. Thank you. That makes sense. I think Simon wanted to say something.
Yes, I enjoyed your talk. You mentioned at the beginning, to do with the vacuum, the challenge of maintaining the vacuum for 100 years. I'm not sure if you mentioned strategies for achieving that.
Yes, but if I understand the question correctly, do you mean the strategy for developing vacuum in a single vacuum insulation panel, or do you mean at the building scale? But what's the exact question, Simon?
So the performance depends on the maintenance of a vacuum, but depending on how it's been made, it may be that the vacuum deteriorates over time, so it has to be, in quotes, topped up, or it's going to be very demanding to have a system which maintains its vacuum over years, decades, or the 100-year challenge that you mentioned. So if you take double glazing, there's a major problem there, that the double glazing deteriorates after 20 years. They can't even maintain the, that's not even a vacuum. That's really the special gases in double glazing, and those seals can't be maintained, and that's more an exchange being contaminated by conventional air that reduces the efficiency of double glazing. So given that you did mention the need to maintain the vacuum to achieve the thermal performance, can you say anything about how that problem is going to be approached?
Yes, this has been something which has been researched a lot, and also now innovatively there are products available off the shelf as well, which assure life for vacuum insulation panels for up to about 80 to 100 years. So what they do is they use PET sheets, for example, which are metallized with some ceramic ceramics, and then these have very low water vapor transmission and air transmission or oxygen transmission rates, so that the vacuum could be maintained to up to about 100 years. So what we're talking about is the leakage of air to inside by increasing pressure only at a rate of 1 millibar per year. You start from about 0.05 millibars per year. So at the 100th year as well, then still the inside pressure will be about 110 millibars, which is very low if you look at the curve, which is S curve for the conductivity in the case of vacuum insulation panels. But then there are problems with PET because this plastic melts at about 140 degrees centigrade or even slightly higher. And they wouldn't perform in the case of fire events that happened in a apartment building in London, for example. So then now we're looking into developing completely metal foils as envelope barrier for VIPs, which is, for example, stainless steel is being looked into these days by us. Yeah, there are solutions, but then every day you find a new challenge. Now, like for example, we're looking into completely fire resistant VIPs.
Yeah. Thank you. Thank you. I think Savas had a question.
You're provoking him. You're provoking him.
No. He had his hand up, but I jumped in. But maybe not anymore. Are there any more questions by anybody, please? No.
Thank you very much, Maria, for everything. It was excellent sessions. I enjoyed it very much.
Thank you very much to
And
all
thank you,
the
Harjit. Very good presentation.
speakers, and Mohamed and Ioana and Simon and Seyed and Kangkang, and of course Harjit, the last one. Thank you for keeping on time. We are only 6 minutes late, which is a great achievement with 6 presentations. And there were some very nice questions. I learned a lot, and I will probably be approaching a few of you with some questions later on. So thank you. And I don't know if Savas would like to say a few words.
Maria, thanks very much for sharing. And also I would like to thank Tassos as well. For the excellent sort of chairing of the session today. Would like also to thank all the attendees and of course the presenters. I mean, as you said, presentations really over the day were very interesting and very professionally done. So I enjoyed the sessions, and I hope they'll provide sort of opportunities for and ideas for collaboration. So again, thank you all for spending the whole day today, and thanks again, Maureen and Seb, for organizing the event. So enjoy the rest of the day. Thank you very much.
Okay, thank you very much. Bye all, and thank
Bye.
you. Thank you.